All right, let's dive into something we all see every day. I'm talking about dissolving. We're going to uncover what's really going on when something seems to vanish right before our eyes. It's more fascinating than you might think.
Most people think dissolving is like magic, poof, gone. But it's really about transformation on a tiny, invisible scale.
So it's not really disappearing.
Not quite. Think about what happens when you add sugar to a hot drink. You stir it, and it seems to vanish, right? But does it really?
Well, the drink gets sweeter, so it must be in there somewhere, just hiding.
Exactly. It breaks down into tiny particles, so small we can't even see them. And those particles spread evenly throughout the water. That's what dissolving really is. It's creating a special mixture where one substance spreads out in another.
So like it's blending in, becoming part of the liquid.
Yes, exactly. And there are specific terms we use for this. The substance that dissolves, like the sugar, is called the solute. The liquid that does the dissolving, like the water, is the solvent. And that final mix, your sweet drink, that's the solution.
Okay, so solute, solvent, solution. Got it. So is it like a tiny party in my cup?
Well, yeah, kind of.
Mm.
It's about creating this uniform blend, a homogeneous mixture, where you can't tell the solute and solvent apart anymore. They become one.
Interesting. But, I've always wondered, does everything dissolve in everything? Like, what if we try to dissolve things other than sugar? Would it work the same way?
That's where solubility comes in. And the answer is no, not everything dissolves equally well in all liquids.
So some things are just meant to be together and others just won't mix.
Right. Think about that experiment, where we mix different substances with water, like table salt, flour, and pepper.
Oh, yeah. The salt disappeared, but the flour got all clumpy and the pepper just kind of floated on top, no matter how much I stirred.
Exactly. That shows solubility in action. The salt is soluble in water, meaning it dissolves completely. Flour is kind of in between. It partially dissolves and makes the water cloudy. And pepper, well, pepper is pretty much insoluble. It just doesn't want to mix with water.
So it's kind of like each substance has its own personality when it comes to dissolving.
That's one way to think about it. Now, have you ever tried making iced coffee by just adding coffee grounds to cold water?
Oh, yeah. It takes forever.
That's a perfect example of how the rate of dissolving can change things.
Oh.
Even if something can dissolve, it doesn't mean it'll happen quickly.
So it's a speed limit for dissolving.
You could say that. And temperature is a big factor here. Think about stirring your hot drink. You're not just mixing, you're also helping the sugar dissolve faster.
But wouldn't stirring just move the sugar around? How does that actually make it dissolve faster?
Well, when you stir, you create more contact between the sugar particles and the water molecules.
Yeah.
It's like giving them more chances to interact.
So more collisions, faster dissolving.
Right. And remember that experiment with the hot and iced water and the sugar.
Oh, yeah. The sugar in the hot water dissolved so fast. But the cold water, it was like watching paint dry.
Exactly. Higher temperatures give the water molecules more energy, so they move faster and collide with the sugar particles more forcefully, breaking them apart more quickly.
So heat is like a speed boost for dissolving.
Precisely. But here's another thing to consider. What if we kept adding sugar to our drink? Would it dissolve forever?
I mean, at some point, the drink would be pure sugar syrup.
Right. But what I mean is there a limit to how much can actually dissolve?
So, like a point where the water says enough is enough.
You got it. Eventually, no matter how much you stir or how hot the water is, no more sugar will dissolve. That's called the saturation point. It's like trying to fit too much stuff in a suitcase. At some point, it's full.
So it's like that invisible line, no more room at the end for any more sugar.
Exactly. And that saturation point, it can actually move, like depending on the temperature.
Oh, so the amount of sugar the water can hold changes depending on how hot or cold it is?
You got it. Remember how we talked about how temperature affects how fast things dissolve? Well, it affects how much can dissolve too. Usually, you can dissolve more stuff in hot liquids than in cold ones.
So hot water is like a bigger suitcase. It can hold more sugar.
Exactly. Now, imagine this. What if we heat up some water, dissolve a ton of sugar in it, then let it cool down carefully without disturbing it?
So we're like tricking the water into holding more sugar than it normally would?
Yeah. That's what's called a supersaturated solution. It's like it has a temporary superpower holding more solute than it should at that temperature.
That's kind of precarious. Like one wrong move and it all falls apart.
You're right. Supersaturated solutions are very delicate. Even a little nudge, like adding a tiny crystal or something, can make all that extra solute suddenly crystallize out.
So it's like a sugar crash, but in reverse.
Yeah, you could say that. It shows just how unstable those supersaturated solutions are. Dissolving, it's not always simple and straightforward. There's all these interesting twists and turns.
We've been talking a lot about water, but it's not the only liquid out there. Does dissolving work the same way in other liquids?
That's a great question. And the answer is yes, but there are some differences. We call water the universal solvent because it can dissolve so many things, but it's not the only one.
Right, there's more fish in the sea, as they say.
Exactly. There are lots of other solvents, and each one has its own, dissolving power. Think about oil paints. You can't clean those up with water.
Nope, you need something stronger, like paint thinner. And that stuff does not smell good.
That's because it's an organic solvent. It's much better at dissolving things like oils and pigments that just won't mix with water.
So it's like you need the right tool for the job.
Exactly. Depending on what you want to dissolve, you need to choose the right solvent to make the kind of solution you're looking for.
So dissolving is happening all around us, not just in our kitchens.
Absolutely. Dissolving is super important in so many areas, from how our bodies work to how we make medicines. It's a fundamental process.
It makes you realize that something so basic like dissolving is actually incredibly complex.
I know, right? It's amazing. Before we finish up our deep dive, I want to leave you with one last question.
Okay, what is it?
We talked about how temperature usually makes things more soluble, right? More stuff dissolves when the solvent's hotter. But is that always true? Are there any exceptions? Like, are there any substances that actually dissolve less when it gets hotter?
Wow, that's a good question. I'm gonna have to think about that one.
That's what's so great about learning. There's always more to discover.
It's kind of funny. We go through life and never really think about stuff like dissolving. But when you actually do stop and think about it, it's pretty mind-blowing.
It really is. Makes you appreciate the complexity of, well, really simple things we do all the time.
Like making coffee. It's not just dumping hot water on some grounds. It's all about temperature and solubility, even how fast things dissolve.
Remember that experiment? Trying to make iced coffee by just adding the grounds to cold water.
Oh yeah, total disaster. All those clumps, it wouldn't dissolve.
Exactly. It really showed how important temperature is. The cold water just couldn't break down those coffee particles the way hot water does.
So it's not just like a personal preference, hot or iced coffee.
Yeah.
There's actually science behind it.
Absolutely. And understanding that science can help us make better choices, not just with coffee, but even understanding how medicines are made, how they dissolve and get absorbed in our bodies.
It's like a secret code to the world around us. The more we learn about these basic processes, the more we understand how everything works, from our kitchens to, well, our own bodies.
Couldn't have said it better myself. It's like we went on this journey, right? Like shrunk ourselves down to see those tiny particles interacting.
We started off thinking dissolving was just stuff disappearing. Now we know about solutes and solvents and solutions and how solubility is like what was it? A dating profile.
Right. And we learn how temperature speeds things up or slows them down.
Oh, and we can't forget about supersaturation, pushing those solutions to the limit.
That was pretty cool.
I think it's safe to say we've dissolved any wrong ideas we had about this whole process.
I think so too. We really got into the nuts and bolts of dissolving, all the details.
So next time you see something disappear in a liquid, remember, it's not magic, it's science.
Exactly. Even in the simplest things, there's all this amazing stuff happening.
Well, I think we've reached our saturation point for today.
Yeah, I think so. But before we go, remember to keep exploring, keep asking questions. There's so much to learn out there.
And who knows, maybe you'll find those exceptions to the solubility rules. So until next time, keep dissolving those boundaries of knowledge.